There are two main rules that we talked about when looking at probability. We have the addition rule and multiplication rule. So the addition rule, there's kind of two scenarios here. If A and B are disjoint, or you could think of this as mutually exclusive, so that means they cannot happen at the same time. When we're finding the probability of A or B, we would just take the probability of A, add it to the probability of B. If A and B are not disjoint or not mutually exclusive, meaning they can happen at the same time, our formula stays generally the same, but there's one slight change here. So if I'm finding the probability of A or B, I'm going to take the probability of A, add it to the probability of B, and then I need to subtract the probability of A and B, which we often thought about as the overlap. If they are not disjoint, they happen at the same time, there's going to be some kind of overlap between the two events. I want to make sure that I always subtract that overlap so I'm not double counting one option. So here's a quick example. It says in a bag there are 4 red marbles, 3 blue marbles, 2 yellow, and 1 green. We want to find the probability of picking a red or a blue. So since I'm looking for red or blue, notation-wise, I would write it as probability of, for red, I'm just going to use R, or blue, I'll use B. So I'm going to start with splitting it up here. So I'm going to take the probability of a red marble and add it to the probability of a blue marble. I always like to put this subtraction. In some cases, there won't be an overlap, so that subtraction will just be 0. Okay, let's go ahead and start with finding the red. Looks like there are 4 red marbles out of 4, 5, 6, 7, 8, 9, 10 in total. So 4 out of 10 for my chances of picking a red. Plus my chances of a blue marble were 3 out of 10. And here's where I would think about whether they are mutually exclusive or not. This is a good example of mutually exclusive events because I cannot have a marble that's both red and blue. It has to be one or the other. So what are the chances that you have a red and blue marble? Well, here it would technically be 0 out of 10. Since we don't really need that 0 out of 10, that's why we don't need this subtraction when we're looking at disjoint events. Okay, 4/10 plus 3/10 is going to give me 7/10, which is just 0.7. So addition rule again is always for when we're finding or. Or is addition. Switching gears, looking at multiplication rule. Our multiplication rule we will use for and problems. So instead of thinking about whether these events are disjoint or mutually exclusive, we're now going to think about whether they are independent or dependent. So if A and B are independent, meaning that the outcome of A has no impact on the outcome of B, when we're finding the probability of A and B, we're going to take the probability of A, multiply it by the probability of B. If A and B are dependent, so that means the outcome of A impacts the probabilities in outcome B, this typically happens when you are not replacing. Okay, for example, if I pick a card and then I don't replace it, and you pick a card, your probabilities are impacted by what card I got. There's only 51 cards now left for you to choose, and you have, your probabilities are different depending on what card I have in my hand. So anytime that you are not replacing something, chances are those events are now dependent. If we're looking at dependent events, when we find the probability of A and B, we'll start with the probability of A, but then we have to have a little conditional probability here. So this says that we're finding the probability of B given that A already occurred. So our example says the flashlight has 6 batteries, 2 of which are defective. If 2 are selected at random without replacement, find the probability that both are defective. Okay, so I'm looking for 2 defective batteries here. So the first battery I choose, there's 2 that are defective out of 6. So my first probability would be 2 out of 6. Now we are going to assume that this happened. So in my hand I have a defective battery, which means there's only 5 batteries left. How many of them are defective? Well, I already have 1 defective in my hand, so I'm left with only 1. I am multiplying here because I need both of these things to happen. I need 1 to be defective and the other one to be defective, so that should be multiplication. You can use your calculator from here. And we get 0.0667. Okay, if we did this same exact problem, but we did it with replacement, so let's say that was part A, and we'll do part B with replacement. Here's how some things would change. Okay, the first battery I'm still doing just 2 out of 6. There's 2 defective out of 6. So I take the battery, I look at it, I'm like, okay, cool, it's defective. I put it back, and now I'm going to choose another one. What are the chances that that second one's defective? Well, I put the battery back, so there's still 2 out of 6 that are defective. So it's really that second fraction that is impacted when you have replacement versus not replacement.